Hey guys, now welcome to the second part of this load frequency control video. So in this video, I would like to further discuss all the technical aspects and problematic aspects regarding load frequency control that generally you will be coming across in examination. So our primary discussion was about automatic generation control. So what is automatic generation control in a power station basically? So automatic generation control is such a control in a power station. So I was already telling you in the last video itself, there are two important parameters in power system that needs to be constantly monitored and or corrected. What is that? Voltage and frequency. So where do you get the voltage and frequency? From the from the generator. Generator will generate the power at some voltage and some frequency. So it is very much important to control the voltage and frequency. And why does the necessity to control voltage and frequency will arise? Only if there is mismatch between active power generation and demand, and reactive power generation and demand, isn't it? So to do that control, there are basically two techniques to do such kind of a control. So let us see, why do we have to get the need of frequency control? So whenever the active power generated is not equal to the reactive power or active power consumed or active power demand, then you will have to control the frequency control is necessary. When reactive power generated is not equal to the reactive power demand, then what has to be controlled? Voltage has to be controlled. So a real-time power system is a very dynamic system. That means the active power generation fairly remains constant, but demand keeps on varying, because you never know who is going to switch on the load or who is going to switch off the load, isn't it? Therefore, it is our duty. We cannot compromise the load. We cannot say a consumer, hey, shut down your load, my frequency is going to fall down. No, you cannot going to disturb the consumer. So what is that we are going to do? We are going to disturb your generation aspect only. So this is called as primary control mechanism. So control of voltage or frequency can be done in two ways. One is called a primary control mechanism. Second one is called as a secondary control mechanism. In primary control mechanism of voltage and frequency control, you have automatic generator control. That means at the generator only you will perform this control. That means you will try to match the demand by varying the generation. But under the emergency condition, when it is not possible to control at the generator, then what we have to do? Then control at the load only. That means like load shedding or load management, whatever. So you have to cut off the load or increase the load, whatever. So that is called as load side management, and that is a secondary control mechanism for voltage and frequency. So as I was telling, automatic generation control is such a system where you are able to control voltage as well as the frequency of the system. So I can say automatic generation control is equal to load frequency control LFC plus excitation control. Why is it called excitation control and load frequency control? So load frequency control is that control mechanism which will control the varying frequency, and excitation control will control the voltage of the generator. By controlling the excitation, basically we are going to control the reactive power generation. If you are controlling the reactive power generation, automatically the voltage will be controlled. Even in load frequency control, you are going to control the active power generation, therefore the frequency will be controlled. Now the diagram which you are going to see here, which is present over here, is the block diagram for a general automatic generation control, AGC control. This is called as AGC. AGC means automatic generation control. Now you see, what does this block diagram has? Now see this diagram of automatic generation control. So what is there in this diagram? At the center you have the generator which is generating active power PG, and this active power as well it is generating reactive power also, and there is also voltage generated VG, and it is having a frequency of FG. Now where this generator is getting input power from a turbine. Now turbine is getting an input power from a boiler. So while the steam is coming from the boiler, I am going to place a governor valve. This is the valve which is going to control the steam input to the turbine. So based on the load requirement, we will be adjusting the steam. So now when active power is being delivered into the bus, there is a comparator over here. So this comparator is receiving the frequency. So the frequency from the outgoing of the generator will be sensed. The frequency sensed is FG. So that will be fed to a comparator over here. To this comparator, I am already giving a F reference. I am giving a reference frequency or the frequency which has to be maintained, and the difference of this, if there is any difference between reference and generated frequency, there will be an error signal generated, and that error signal will appropriately operate the generator valve. So this loop of controlling the frequency with the generator valve and this kind of a closed loop system is called as the load frequency control loop. So this closed loop is called as load frequency control loop. So one important characteristic of load frequency control and excitation control is that the time of response of excitation control is more faster. That means excitation controlling of voltage is very easy or very fast as compared to control of load frequency. Why? Because now you see, load frequency is involving what? Load frequency is involving governor valve, turbine, steam from the boiler. That means mechanical aspects, mechanical parts are included over here. Mechanical parts means automatically the weight or the inertia, the mass of these components are high. That means automatically the time constant will increase. That means the response, now you are going to feed with some error signal, means it will take the time, it will take for some time for the governor valve to respond open and turbine to change its speed or its torque according to the input. Therefore, there is a time constant, a heavy time constant involved in mechanical system. But whereas what is there in this excitation control, see, simply there are some electronic circuits. So electrical time constants are always less than the mechanical time constant. So I can also write one conclusion over here. So response of excitation control is faster than load frequency control. Please note this important point. So this may be asked in MCQs, in theoretical MCQs. So why is it so? Because the time constant of mechanical systems will be higher than the time constant of electrical systems. So mechanical time constants are always higher than the electrical time constant. Therefore, excitation control response is much faster. It happens in only seconds, within seconds, whereas it takes minutes, for a few minutes to tens of minutes for load frequency control to control or stabilize the frequency of the system. Okay, now let us see about this frequency error. Okay, error signal of the frequency. So this error signal of the frequency is given by Fg minus F reference. Okay, so this is the configuration of Fe. So let us see three cases. If the generated frequency is matching with the reference frequency set, what happens? This valve opening should be varied, because this error signal is fed to the governor valve. So governor valve will be varying based on this error signal. So valve opening is constant. Let us say the valve is opened a little bit, some amount of steam is flowing, and that opening will remain constant as long as the frequencies is same. That means if both frequencies are same, is what? Error generated is equal to 0. So there is no action on the governor valve. Next case you will see. In next case, if the generated frequency is higher than the reference frequency, now what happens to the error? Error is positive. If error is positive, frequency is greater than the reference frequency. Frequency is rising, means what happens is valve will close. Valve closes until Fg equals to F reference. That means until error becomes 0, the valve will close. Why is it so? Because the generation, that input power is more, but there is no output from the generator. So what happens? Automatically the speed of the generator rises, hence the frequency will rise. Therefore the valve will be closing until the frequency falls to the normal value. Next case is if generated frequency is less than the reference frequency. Okay, that means frequency is falling, means more loading is there in the system, isn't it? So what happens to the error signal? Error now becomes negative. When the error becomes negative, means valve will open further, even more it will open until the error becomes 0. So in this way, this error signal will be controlling the governor valve, and in this fashion load frequency control mechanism will be functioning. So next concept that we will see is the basic component of this load frequency controller is this governor valve. So this governor valve has got a mechanism, or the example for this governor valve mechanism is called as fly ball mechanism. Okay, so this is very important, or MCQ basically. So the mechanism used in governor valve of load frequency control is fly ball mechanism. You might have already seen the fly ball mechanism or governor diagram in your graduation level, but we are not going to discuss about that. We will straightly jump into the what is required for the examination. Now in this section, now I am going to define a parameter called as a speed regulation parameter, which is usually given by a letter R. So what is this speed regulation parameter R? So this R in load frequency control is defined as minus of delta F by delta P. So what is the unit of F? It is hertz. What is the unit of power in a power system level or in this generator level? Basically megawatts. So the units for this particular regulation parameter R is hertz per megawatt. Okay, so what does this basically signify? So it is showing you something delta F and delta P. Delta F is nothing but change in frequency when the machine is operated from no load to full load, and delta P is nothing but change in loading on the generator from no load to full load. That means this delta P which I am telling, I can also say the rating of the machine, because always the rating of the machine is its full load capacity, isn't it? So let us draw a graph against frequency and power over here. So power here is 0. Let us say the rated capacity of this particular generator is somewhere over here. Let us say this is P1. P1 is the rated capacity of that particular generator, and when there is no load on the generator, load is 0, the frequency at that time is F0, that is no load frequency. Generally no load frequency is 50 Hertz. Okay, no load frequency is 50 Hertz. Now as you keep on loading this machine, what happens? Automatically the speed will be decreasing, assuming that there is no governor as of now. Okay, there is no load control mechanism or frequency correction mechanism is not there. So what happens? The frequency keeps on falling like this, isn't it? So what is the change on frequency now? What is the change in load? How much load you will apply on this particular generator? Maximum up to its full load rating only, no? Up to P1 only you will be applying the maximum load. So during this period, what is the change in frequency from no load to full load? Okay, let us say the initial frequency was something F0, and now here is the frequency settled FF, where FF is the frequency under full load condition. Now change in frequency, what is the change in frequency over here? This only, no? Delta F. So this delta F is the change in frequency from no load to full load. Okay, simultaneously what is the delta P here? Change in the power output from no load to full load. This is only the delta P means. Okay, so I hope you understood what is delta F and delta P. So let me write down here, delta F is nothing but no load frequency minus the full load frequency generally. Okay, now next see, I am defining another parameter called as the speed regulation constant. So always the speed regulation constant will be given in R. Okay, always the speed regulation constant will be given in percentages. So before this, another thing I want to highlight over here is this R is constant for every generator. That means constant for a given generator, R is constant. Okay, R is constant for a given generator. That means if R is constant means I can define one formula, that is delta F1 by delta P1 should be equal to delta F2 by delta P2. Okay, please remember this particular formula. This is very, very helpful and it saves a lot of time, especially when you are supposed to do some numericals on this questions or on this topic. Okay, next we will define speed regulation constant. So speed regulation constant is a percentage, whereas speed regulation parameter is some value having hertz per megawatts as the units. Okay, so speed regulation constant is a percentage. This percentage is nothing but it shows the percentage of variation in frequency. So it is the delta F ka percentage. So what is the delta F percentage? The percentage of delta F is nothing but the percentage change in frequency is nothing but delta F. Okay, delta F means change in frequency by the no load frequency F0 into 100. So this is only the speed regulation constant. So speed regulation constant percentage is nothing but the change in frequency, okay, as with respect to the no load frequency into 100. Let us say a particular generator is having, example, 2% speed regulation. A generator is having 2% speed regulation and its operating at no load frequency is 50 Hertz. So what is the change in frequency when it loaded fully? So simply you can tell from 2% you can find out what is delta F. What is 2% delta F is equal to, if you want to find delta F, okay, from this formula you see, to find the delta F, that will be equal to percentage into frequency not by 100, isn't it? So what is the percentage? 2% by 100 into what is the full load frequency or no load frequency? 50. So that is equal to how much? 2 ones and 250, that is 1 Hertz. So the change in frequency delta F is 1 Hertz. That means the frequency under full load condition will be no load frequency minus the change in frequency, that will be equal to how much? 49 hertz. Okay, so that is what the meaning for this 2% regulation means. Whenever you find 2% speed regulation means it is going to indicate how much the frequency is going to vary with respect to no load frequency. Okay, from no load to full load. Next we will see one question. Let me read out this question. A 200 megawatt turbo generator is having a speed regulation of 8%. How much turbine input is to be increased for steady state operation for a frequency drop of 0.05 hertz? So let us see what is the given data over here. So he has given the frequency drop. So what does frequency drop means? Delta F value has been given. How much it is? 0.05 hertz. So first we will find out what is the regulation parameter for this particular generator. So regulation parameter is nothing but R. So I am just taking the mod of R, that means positive R. So that will be equal to delta F by delta P. I mean change in frequency by change in the power. So what is the change in frequency from no load to full load, or delta F is given in the question only as, is not given in the question. He says that it is now like that, but as per the regulation constant you have to take, see always regulation parameter, regulation constant, this R, regulation parameter R is defined from no load to full load. Please keep this in mind, don't get confused. No load to full load. Okay, so what is the change in frequency from no load to full load? That is specified, this 8%, isn't it? So 8% of the no load frequency. So what is no load frequency? It is not mentioned. So when in the question not mentioned, this is India we are. So therefore take 50 hertz as the no load frequency. So 8% of 50 hertz is the delta F from no load to full load. And what is the change in frequency from no load to full load as per this regulation parameter R? That is the rating of the generator, isn't it? From no load to full load, from 0 megawatts to 200 megawatts is the maximum full load capacity that it can be taken. So 200 megawatts. Okay, 200 megawatts. So upon solving this, 8% of 50 means 8 by 100 into 50 by 200, that equals to 4 by 200 or 2 by 100 or 1 by 50 hertz per megawatt. So I got the regulation constant as 1 by 50 hertz per megawatt as the answer. Okay, next he is asking you how much power input has to be increased. How much power has to be increased if the frequency drop in the system is 0.05. If the frequency is decreasing in the system means, if I want to pull back the frequency means what I have to do? I have to put in more power, isn't it? So that I can find out from that relation that we have made here. Regulation constant remains always constant for every generator. Then I defined one formula in this way. Delta F1 by delta P1 will be is equal to delta P2 by delta F2 by delta P2, isn't it? So delta F1 is the initial case. Initial case is nothing but the rated values. So delta F by delta P or delta F1 by delta P1 is this initial case. So that is 1 by 50. So delta F2 is what is given, for which you have to find out what is the change in power P2. So from this I can write down this delta F1 by delta P1 is already found, that is 1 by 50. So let me write out in this side. So 1 by 50 is equal to delta F2 is nothing but 0.05 hertz as given. So delta P2 is to be found out. So that will be equal to delta P2 equals to 0.05 into 50. So that can be written as 5 by 100 into 50. So this get cancelled out, then you will get how many megawatts? 2.5 megawatts, which is option number A over here. So option A is the correct answer for this question. Now we will see the block diagram representation of this so-called speed governing system. This is important for us. So if you see this block diagram, there are three important blocks over here, and each block represents an first order system, first order transfer function. Okay, so this first block represents the governor valve. So immediately after the governor valve, what you will have? You will have a turbine mechanism, turbine. So from the turbine again you have the generator. So between turbine and generator there is a summiter which is taking another power as as a feedback, minus PD. So this PD is nothing but change in load demand, because when you are supplying power, active power on the generator, the demand is varying. So how much is the demand varied? That is the signal coming. This is called as PD. So this is called as the demand change, and the output of the generator is like this, and this output is delta F, okay, change in frequency. So if there is any change in frequency, that change in frequency will be sensed by this block 1 by R. Okay, this feedback sensor, okay, this is a feedback path, isn't it? This is a negative feedback. So 1 by R becomes a negative feedback sensor to this entire control system. Now, what is the unit of R that we have already seen? The unit of R is hertz per megawatt, isn't it? Now, what is the input to this R? Change in frequency, isn't it? The delta F is the input to the R. The delta F is the input to the R. If delta F is input to the R, means you are multiplying frequency with R, means hertz into hertz per megawatt. So R is hertz per megawatt. So 1 by R is megawatts per hertz. So megawatt per hertz and hertz get cancelled out. Then what do you get? Megawatts. That means you are going to give one signal to this comparator over here. How much difference power has to be included or removed from the input so as to balance the frequency. Why? Because the active power is being generated here, or the active power supplied by the turbine is here, the mechanical power supplied by the bus, by the turbine. But if ever there is any change in the demand, that means input power and output power, if there is any change, then the difference or the change in frequency will be appearing through the generator block, and this is the delta F is the change in that frequency. Now again, that change in frequency is sensed by this 1 by R. He is converting the frequency signal into power signal. That means the units of hertz, see, just before this block the signal units is hertz. Now after transforming to this block, what is the signal? Megawatts. Now the signal is megawatts, power signal is the megawatt. Now you see to this summator, what is the input? Delta PC, where delta PC is nothing but it is called as speed governor setting. Please keep this man, delta PC. Directly he will ask in MCQs, delta PC in a flyball mechanism or speed governor system is called as speed changer setting. To this block another power is input, that is delta P tie line. That means tie line power change in incremental change or change in tie line power. Why? Because now assume that this is an interconnected power system. So if this is an interconnected power system, to this particular power system, you are having, let us say there is a generating station like this, and this generating station is connected to its own bus, this bus, let us say this is G1, and the bus of this generator 1 is bus 1, okay. Let us say there is another generator G2, okay, and it has got its own bus number 2. Let us say this is an interconnected system. Interconnected system means the generator buses will be generally interconnected, isn't it? That means some power will be exchanged through the tie line also, depending upon the value of delta at the generators. Let us say for this generator I am studying the speed mechanism. That means there is tie line power also input, no? So I have to consider the existence of tie line power also. Let us say if this is not a interconnected system, then you can set this delta P tie line is equal to 0, okay. And whatever is arising out of this block is called as ACE, which means area control error. So I am writing it, area control error, okay, ACE. So ACE is equal to, ACE can be defined in what way? The sum of speed change setting plus tie line power increment minus, okay, this delta P, okay. Delta P is nothing but, I will write it just in terms of whatever is given here. So delta F by R, isn't it? So this is what called as area control error equation. This is called as area control error equation, okay. Let us say this kind of a controlling mechanism is automatic control mechanism. So how do you basically control? So now you see, now area control. So whenever this error has been raised, now which one has to be varied, or which one we have to control? We have to control the speed change setter. Basically what is in our hand is speed change setter delta PC. If you are varying delta PC only, then only you can vary the frequency. Basically that thing you have to keep in mind, because delta P tie line or tie line power is not in your hand. Tie line power is from the external network, okay. So to control this delta F, you have to control the delta PC, okay. Please keep that in mind. So regarding delta PC, there are some other terminologies or some other MCQs or some bits or points that you have to remember. That is, if delta PC is equal to 0, let us say in a speed governor mechanism, delta PC is equal to 0. That means there is no change in speed change setter. That means you are not controlling the steam valve, simply I can say you are not operating the valve. That means the valve opening is remain constant. So if you are going to study the behavior of change in frequency under this condition, that is when you are not operating the valve, that kind of operation is called as free governor operation. Free governor operation. And this is the assumption before doing this load frequency control analysis. We will, throughout the load frequency control analysis, we will assume that it is free governor operation. That means you are not going to see how much is the delta PC change. Okay. Next thing that I want to highlight over here is, if this control of frequency, if this is an automatic load frequency controller, that means the delta PC, everything will be adjusted automatically. Let us say if it is an automatic system, under automatic system, this delta PC will also remain constant. So if delta PC is constant, means I will simply modify for automatic load frequency control, ACE, area control error, is equal to P tie line minus delta F by R. Okay, for automatic load frequency control system, this is the area control error. So this factor over here, 1 by R, is defined by one letter B, which is called as bias coefficient. Please remember, bias coefficient is nothing but 1 by R. That means I can write the area control error in terms of bias coefficient in this way. That is delta P tie line minus B times of delta F. Now let us see that some load disturbance has taken place on this generator, therefore delta F came into picture. That means let us say frequency has been reduced. So let us see how the frequency is varying with respect to time, and how, if the governor action is coming into place, how the frequency has been balanced. Let us say this is the rated frequency or no load frequency, this point over here, and this x-axis is time, as time is going forward. Let us say at time t is equal to 0, some disturbance happened on the, or load on this power system has suddenly increased. So what happens? The frequency started to fall down. So after a certain time delay, the governor started acting. Okay, we have started the governor operation to normalize the frequency. So what happens? The frequency starts going up, and let us say the frequency will overshoot, and it will oscillate. The frequency oscillate, and after some time will oscillate, and after some time it will settle at one fixed value. It will settle at some fixed value. But it was observed that after the corrective action, after the frequency correction, the settled or the final steady state value is slightly different from the rated value. That means still there is some error like this here. How much? Some delta FSS, where delta FS is nothing but the steady state error in the frequency. This is called as steady state frequency error. So we have observed that there was some steady state frequency error. So how do we reduce this steady state frequency error? So to reduce this steady state frequency error, so if you assume, if you make the control system analysis of this given block diagram, what it was found that if you make a small addition to this control system, that too in this feedback loop, then we may try to increase, or we can try to reduce the steady state error. So what we have done is, we have added another integral controller whose gain is given by in this way. Okay, you are adding one integral controller. If you are adding an integral controller to this existing system, then the system behavior was in this way. So the behavior of the system was like this. That means the steady state error has been removed. So this graph represents without integral controller, and this indicates with integral controller. So one very important question is, to eliminate steady state error in the frequency, which controller has to be used? So integral controller has to be used. Integral controller in LFC, in load frequency control, eliminates steady state frequency error. Please note down this point in your book, very important point. Now we have now concluded that even after using a controller or load frequency controller, after the control action has been taken place, we have found that there was some steady state error or frequency drop existing in the system. To eliminate that steady state error, we have to use a proportional or integral controller. We have to use an integral controller. Okay, basically, so we have to use an integral controller, as I told you. So assume that there is no integral controller over here. If there is no integral controller over here, now there will be some steady state error or steady state difference or frequency drop in the system. So now the questions will be framed in this way. Now he will ask you to find out what is the frequency of the system after the load frequency control has been taken place. Okay, after the governor action has been taken place. Okay, so this steady state frequency error is nothing but, okay, this F steady state frequency drop is defined as, so this is the frequency drop after the compensation of frequency. Okay, so that will be given by F new. So new frequency after the correction minus F naught, that means the rated frequency of the system which has to be there. So this is called as FSS, frequency steady state error. Okay, this, please remember this equation, don't get confused, don't put F naught and F new over here. Always new one should be in the first and old should be in the last. This old is nothing but the rated frequency. Okay, now this question may be asked in basically 3 different cases. So what are those 3 different cases means? First case that we are going to see is an isolated generator. Isolated generator is a simple generator, one generator feeding some group of loads, that's it. Number of loads but fed by only one generator, that is called as an isolated generator. That means a generator which is not connected to the grid is called as isolated generator. Now in isolated generator there are 2 cases. What is that? One case is rise in demand. Rise in demand means load increase. Load increase means I can say delta P D is increase, isn't it? So this is one case. Next case is decrease in demand. So the formula for the change frequency in case of rise in demand case is given by the F new is equal to F naught, which is the original frequency, or I can say the rated frequency of the system, multiplied by H into S minus delta PD into TD divided by H into S, close bracket, to the power of 1 by 2. So you just put, let me just put in bracket over here. For in case of decrease in demand, what happens? The frequency will rise. Okay, so that new increased frequency would have been equal to, after the corrective action, H into S minus delta PD into TD by, this is another important frequency. So let me define the variables involved in this equation. So here this F new is, the frequency after the corrective action. F naught is the rated frequency of the system, where H is nothing but the inertia constant, which is given as in megawatt seconds per MVA. That is inertia constant. And S is nothing but rating of the generator, which is given in MVA. Okay, TD is there. TD is nothing but time delay in governor operation. So this parameter will be given in the question only. Okay, so because governor is a mechanical system, it takes some time to operate. So what is the time delay? It is given in seconds. And delta PD is change in load, which will be given in megawatts. Okay, unit is megawatt. So these are the 2 cases of isolated generator where you may be asked to find out what is the steady state error. So you may find out the F new. From this you must subtract the old or the original frequency, then you will get the steady state frequency. So the next case is when the generator is interconnected, when the generator is interconnected. So the next case is area control. Area control means controlling the frequency of one particular area, because area is nothing but interconnection of a group of generators belonging to one same state only. Okay, so that means interconnected operation. What is the steady state frequency? That is the concept that we are going to see. So that change in frequency with area control is given as delta F is equal to minus of delta PD, okay, minus of delta PD divided by a factor D plus 1 by R. So this is the change in frequency after the governing action in area control case, where PD is nothing but the change in demand and R is the regulation parameter and D is called as load frequency constant, or it is also called as damping coefficient. So let me write down, explain each individual parameters. So PD is nothing but change in demand. So one important point that you have to take care with respect to PD is, if PD increases, that means demand increases, then it should be taken as positive. If demand falls, it should be taken as negative. Please pay attention when to take positive and when to take negative. That is about PD. And next we are having D. So D is nothing but it is defined as change in power by change in frequency. So dou P by dou F. So the units for this is megawatt per hertz. This is also called as load frequency constant, or it is also called as damping coefficient. And You know what is R means? R is nothing but regulation parameter, which is given by hertz per megawatt. So that is the steady state frequency error related formulas. Now let us try to apply this concept in one problem. The question says an interconnected power system is having 1500 megawatt at 50 hertz. That means some generator is having in that way. Frequency is changing at the rate of 2.5% for a load change of 1.5%. That means if load changes by 1.5%, frequency is changing by 2.5%. It seems. Calculate the steady state frequency drop if a 200 megawatt industrial load is tripped. Assume regulation parameter some 0.005 hertz per megawatt. So he's asking you to find out what steady state frequency drop, and for which case? Interconnected power system case. And I hope you remember the formula. What was that formula? Equal to delta F is equal to minus of delta PD divided by damping coefficient plus 1 by R. Now you know the what is PD, change in load. What is the change in load? 200 megawatt, and 200 megawatt tripped off, that means removed. That means 200 megawatt is been removed. If the load is removed, what should be the PD, positive or negative? Negative. So minus 200 megawatt is PD, and you know the rated frequency or F0 of the system, that is 1500, and rated power of the system is 50 hertz. Okay, rated power is 1500 megawatt. Now you have given the value of R also in the question, that is 0.005. Now you should find the value of D. So we have already defined or set the value of D is equal to dou P by dou F, where dou P by dou F is nothing but change in frequency by change in power by change in frequency. So this is directly given in the question only. So in the question, what is the change in frequency? 2.5% change in frequency. Okay, and change in power is 1.5%. So I can write 1.5 into 1.5% by 100 into system power is 1500 divided by 2.5 by 100 into frequency is 50. Okay, so this can again be written as, this becomes 3 times, and this is, so after solving I will get D is equal to 18. So I will substitute all the values as given here as per the formula, and then I will get 0.917 hertz is the change in frequency. Can you tell me what is the new frequency now? The new frequency is increases definitely. The new frequency will be equal to delta F plus original frequency, that will be equal to 50.917 hertz. So the frequency has been increased. Why the frequency will increase? Because an industrial load is stripped off, 200 megawatts has been removed, automatically the frequency will rise. So this 0.917 is that steady state error. Next question we will see about the isolated generator operation. A 200 MVA turbo generator is operating at no load, okay, and if a load of 70 megawatts is applied to the generator, that means load has been increased, PD, delta P has been increased, and that is equal to how much? 70. Now you are asking to find the steady state frequency error drop or steady state frequency drop and the new frequency if there is a delay of 0.5 second in the governor system, and he is asking you to assume that inertia constant is equal to 4 megawatt second per MVA. So let us write down the given data. The given data is PD is been given how much? 70 megawatt. He has given you the value of time delay TD is equal to how much? 0.5 seconds, and he has given you the value of inertia constant H is equal to 4 megawatt second per MVA. The rating of the system S is given as 200 MVA. So I hope you remember the new frequency formula. So the new frequency would be equal to the original frequency into H into S. What is this H into S is equal to? Basically that is the kinetic energy of the system. So the load increases means minus change in power into time delay TD divided by the kinetic energy, that is H into S under root 1 by 2. So you know the value of H, you know the value of S, PD, TD, all values are known. You know the F0. Okay, F0 is not known over here, therefore take it 50 hertz as you know. So after solving this you will get the new frequency would be equal to 48.89 hertz. If new frequency is 48.89 hertz, you can easily find out what is the steady state error in the frequency. So the delta F would be equal to automatically 50 minus 48.89, that should be equal to 1.11 hertz. So these are the required answers for this question. I hope you understood about this concept. So when two generators are operating in parallel and how the load is being divided between the two generators and what will be the combination frequency, frequency of the total system. Okay, so that is the general case of questions that will be asked. So in this load sharing of parallel generators, there are basically two situations. The first situation is with different. So when two generators are operating in parallel and how the load is being divided between the two generators and what will be the combination frequency, frequency of the total system. Okay, so that is the general case of questions that will be asked. So in this load sharing of parallel generators, there are basically two situations. The first situation is with different speed regulations. Consider there are two generators operating in parallel like this. This is generator 1 and this is generator 2, G2, G1, and the rating of generator 1 is P1, that is equal to 250 megawatt, and generator G2 P2 rating is another 250 megawatt. Okay, let us say the regulation constant for generator 1 is 4% and the regulation constant for generator G2 is 6% is the regulation constant for this particular generator. These both generators are connected to one common load bus because they are operating in parallel and they are sharing some load over here. Let us say the load supplied by the generator 1 is PA and load supplied by generator 2 is PB. Okay, so the total load that these both generators are together feeding is PA plus PB. Let us say that load is equal to 400 megawatt. Okay, these two generators are together feeding a load of 400 megawatt. PA is the power supplied by the first generator, PB is the power supplied by the load supplied by the second generator. Okay, now I am going to draw one frequency versus power graph for this both generator at one time only, at the same time. So just look at this graph which I am going to draw over here. So there is a graph like this. On the x-axis I am going to take the power, okay, and on the y-axis I will take the frequency. Because these both generators are operating in parallel, I will take them back to back only. Let us say this side I will take for generator 1 and in this area I will take for generator 2. Okay, so when two generators are generally operating in parallel, the no load frequency of the both generators will remain the same. Okay, so let us say this is the no load frequency F0 and F0 is equal to how much for us? 50 hertz. Okay, 50 hertz is the F0. Okay, next let us say this is for generator 1 now. So from no load to full load, so this is no load and full load is nothing but its rating, isn't it? So rating of the generator is P1. So from no load to full load there is some change in frequency for generator 1 as well as for generator 2. So for generator 1 and generator 2, how much is the frequency change? For generator 1 the change in frequency is 4%. If 4% is the speed regulation percentage for generator 1 means what will be the change of frequency? Change of frequency is nothing but 4 by 100 into 50, that will be equal to how much? 2 hertz. That means there will be a drop of 2 hertz from no load to full load. If 50 hertz is the no load frequency, where will be the full load frequency? At 48 hertz will be the full load frequency, isn't it? So this will become the full load frequency, okay, for the first generator, 48 hertz. If 48 hertz is the full load frequency means, so the curve look like this, isn't it? The regulation curve is like this. That means as the frequency changes from no load to full load, the change in load is also from no load to full load. So this much will be there. Okay, so the delta F for the first generator is how much? 2 hertz. Okay, 2 hertz. So like that, if 6% is the regulation constant, then the change in frequency will be 3 hertz. Okay, if change in frequency is 3 hertz means, let us say P2 is the generator capacity, P2. So 47 hertz it will be there, isn't it? The full load frequency would have been 47 hertz. So to reach from no load to full load up to 47 hertz, how will be the graph look like? The graph looks like this, isn't it? The graph looks something like this. Okay, the regulation graph looks something like this. Now I am saying that these both generators are supplying some load of PA and PB. Let us say the load supplied by generator 1 is PA, which is somewhere over here. This is PA, and at the same time load supplied by the generator 2 is some PB which is over here. So from here to here is PB, here to here is PBA, because both of them are sharing the load. So this length between PA and PB is nothing but the total load, total demand, isn't it? PA plus PB. Okay. So the frequency corresponding to this PA operation, okay, the load shared PA will be like this. So somewhere over here, okay. So the same will be the PB shared, okay. Since both generators are operating in parallel, their frequency remains the same all the time. So that is the basic idea of parallel operation. So in parallel operation, always the frequency remains the same. So the load division between the two generators will take in such a way that the frequency remains constant. Now you see, these both generators, when operating with PA and PB load, have a sharing a common frequency somewhere over here. Okay. Now you are supposed to find what is that frequency with which both of them are operating. At the same time, what is the PA and PB of the both generators? Tina? అది చూస్తుండదు, ఆఫ్ అయిపోయిందేమో. వస్తుంది కదా, చూస్తున్నాం అనుకోద్దిగా ప్లీజ్, మళ్ళీ చెప్పిందంత వేస్ట్ అవుతుంది. Now here I want to define one angle over here. Now you see, there is an angle made between this red color line and the regulation graph. Let us say that is theta1, and you see here similarly between this line and also there is one theta1, isn't it? Like this, here also you see between this triangle, okay, let's assume this is a triangle, there is an angle theta2, and simultaneously there is some other triangle like this, and the angle remains the same because they all are parallel angles. Okay, so theta2 only, same angle. So if the angle is same, so I can write for generator 1 like this. For generator 1, tan theta 1 will be equal to, so tan theta 1 for this bigger triangle will be opposite side by adjacent side, isn't it? So opposite side is what? Change in frequency, isn't it? Delta F. And what is the adjacent side? Change in load, no load to full load. So what is the change in frequency? As you know here, 2 Hz is the change in frequency, and change in load is what? From no load to full load, 250. Okay, that would be equal to another small tan theta, isn't it? The small triangle ka tan theta. Okay, the tan theta of the smaller triangle would be equal to what? Change in frequency, which I don't know. Okay, which I have to find out some change in frequency, delta F2. Okay, this delta F2. And what is the change in load? 0 to PA, isn't it? For the smaller triangle, so PA. So both angles are same, means I can equate this both, right? So if I equate both of this, then I will get what? Delta F2 by PA would be equal to 2 by 150. Okay, from this, the delta F2 can be written as 2 by 150 into PA. Okay, take this equation number 1. Okay, similarly I will make the another this same analysis for generator 2 also. For generator 2, you have tan theta 2. So tan theta 2 for the generator 2 will be equal to, let us take the bigger triangle. So tan theta 2 is nothing but the change in frequency. What is the change in frequency from no load to full load? 3 Hz, isn't it? And what is the change in power? 0 to P2, that is rating of the generator, that is P2. Okay, P2 is nothing but 250, isn't it? 250, and that should be equal to what? Tan theta 2 will be equal to the small triangle 1. So for small triangle, tan theta 2 will be equal to what? The change in frequency. Okay, this change in frequency is the same as the change in frequency of this generator, isn't it? Because both of them are operating at the same frequency. So delta F2 by change in power is how much? PB. Now from here, PA plus PB is equal to 400, means I can write PA is equal to 400 minus PB. Okay, now from here I can equate this equation, both parts, and I can say that delta F2 equals to 3 by 250 into PB. This becomes equation 2. Substitute this value in equation 2 and solve. After solving, you will get the values in this way. PA shared will be equal to 240 megawatt and PB will be equal to 160 megawatt, and frequency of the system finally will be equal to 48.08 Hz. So there is an alternative way or fast way to do this. There is nothing magic, the same thing that we have been already discussing. Okay, sir, should we take tan theta? Should we draw this graph all the time? No, you need not draw all the time, because now I am explaining, I am drawing. So let us see what is that another way that we can do. So I have already told you that for a given generator, always the regulation R will be constant. So first to find out the value, what is the value of R? Okay, so from that no need to find the R, you can directly find out what is the ratio that we have defined, that is delta F1 by delta P1 would be equal to delta F2 by delta P2, isn't it? So this delta F1 by delta P1 corresponds to the rated values from, that is no load to full load. So what is the no load to full load change in frequency? 2 Hertz for the first generator. What is the no load to full load rating for the first generator? 250. That is nothing but its generator. Now this is from no load to the required frequency, which I don't know, delta F2. This is no load to the required power. What is the required power supplied now? PA, isn't it? So now I got PA. In the same way I can define for the generator 2 also, and upon solving this without actually having to draw this graph also and taking tan theta, I can directly come up with the conclusions, isn't it? Directly simply solve it, then you will get the value of the required frequency or load. Okay, so that also let me do it. So delta F2 would be equal to 2 by 250 into PA. Okay, and similarly for the second generator also we got delta F2. We will get delta F2 is equal to 3 by 350 into PB. So PB can be written as 400 minus PA. Now this delta F2 of both generators are the same. Change in frequency of both generators is the same. Just equate these two parts. Then upon solving, then you will get those required values, which is PA shade would be equal to 240 megawatt. And PB will be equal to 160 megawatt, and the final frequency of the system, new frequency, will be equal to 48.08 Hertz. So in this kind of problems there is another case that is possible. That case is if the generators are to be loaded without overloading. So before going into that case, we will try to draw some conclusions, some important conclusions from this part only. Now you see, what is the load shared by generator A? 240 megawatts. Load shared by generator B is 160 megawatts. What is the regulation of load generator 1? 4%. For this one is 6%. What did you observe? The generator having more regulation is sharing less amount of load. Generator with more regulation will share less amount of load. So that is the fact. Let us say there are some generators operating in parallel and their regulation diagrams or their regulation characteristics are in this way. One generator is having regulation characteristic in this way. That means there is no change in frequency. That means the regulation is equal to 0. So such a generator whose regulation is equal to 0, that means there is no change in frequency for any change in load. Such a generator is called as isochronous generator. Okay, this will become an important MCQ. Okay, isochronous generator is whose regulation will be 0. Let us say there are 2 or 3 generators like this operating. So one generator is 2%, one generator is 3%. Let us say another generator is 6%. So this percentage indicates the droop, isn't it? The slope of the curve. Let us say this generator has to supply some load of something over here, or these all generators are operating in parallel, isn't it? Operating in parallel means all of them will have the same frequency. So if the frequency of all the generators is same, now you see load shared by the generators are in this way. Now you see the generator which is having 2% is sharing a lot of amount of load, whereas the generator of 3% is sharing only some amount of load. Generator with 3% is okay. Generator with 3% is sharing only this much amount of load. Generator with 6% is sharing this much amount of load. That means load sharing is inversely proportional to percentage regulation. Please keep this point in mind. So the next case would be, what would be the maximum loading on each generator so that each generator will not disturb or they are not driven into unstable without overloading. So the case is the same, different speed regulation, but without overloading of generator. Now let us see the same condition only. Now initially we found that generator A1 was sharing a load of 240 megawatt. Now generator B is sharing a load of 160 megawatt, isn't it? Generator 1 is 240, generator B is 160. Now without overloading the both generators, I want to further add more load to this parallel combination. Understood? So if I'm going to increase the load on the system, automatically the load shared by these both generators will also keep on incrementing. So let it go from 240 and 160 and above, it will be going on. So now you see which one is closer to overloading? Generator 1. Why? Because the capacity of both generators is the same, 250. Already generator 1 is almost near to the full load, 240. So if you increase only up to a further 10 megawatt, then this generator will be overloaded and it is finished. Okay, so you cannot further increase the PB without overloading. So let us say now the PA to be shared by this generator, okay, maximum load that can be shared by the generator would be the same, P1 is equal to PA, and corresponding to this one, what would be the load shared by the second generator? This would be the load shared by the second generator, isn't it? That would become the PB. So this is the P max that can be supplied by two generators having 4% and 6% different regulation characteristics. So now we will see how to find out that P max value and how to conclude with this kind of questions. The load that must be supplied, that can be supplied by these two both generators operating in parallel without overloading themselves. So already we have seen that the generator which is having less regulation constant is already near to the full load. So it can take up to 10 more megawatts. That means now you can satisfactorily load the first generator to the maximum, isn't it? So let us say under maximum loading condition, now the maximum load that can be supplied by this generator is 250. So let us say now the load supplied by the first generator is equal to 250, that is nothing but equal to the rating of the machine. Okay, now if this is the load supplied by the first generator at its maximum, then the load supplied at this condition by the second generator would be how much? Some PB. So you cannot increase the PB or the load supplied by the second generator furthermore. Why? Because if you are going to increase PB, this line is going to shift down, means your first generator is getting overloaded. So always when you want to operate two generators in parallel, the generator with least regulation can be operated at full load, but the other generator will be underloaded. So that can be determined by this kind of a formula or this kind of a situation like this. So I want to find out what is the load shared by the second generator. So again come back to the fundamentals, that is delta F1 by delta P1 would be equal to delta F2 by delta P2. So delta F1 by delta P1 is nothing but the regulation of the first generator. So delta for the second generator, so that is 3 by 250 is equal to change in frequency. So the change in frequency would be the change in frequency for the first generator only, because you see, because the first generator is only getting overloaded, so that would be equal to 2 by, or if you don't know that also you can put just F2 is equal to 2 by P2 is nothing but PB that it can be supplied. So if you solve this, then I will get PB is equal to 166.6 megawatts. That means maximum load that can be supplied with this both generators PA plus PB would be equal to how much? PA is 250 and PB is 416.6 megawatts. So this particular parallel combination can take a load of 416.6 megawatt without overloading themselves. Okay, so now important points to be noted over here is, see, without overloading case means always the generator with least regulation constant will be loaded at full load. Okay, so generator with percentage regulation less will be fully loaded. Change in frequency would be equal to change in frequency in case of first generator. So change in frequency in case of first generator would be nothing but percentage regulation of the first generator by 100 into system no load frequency. Next thing that we have to see is which generator will get loaded first. So the generator with less percentage regulation, that is generator 1, gets loaded first. So these are some important points that may be asked in examinations with respect to this concept. So this much is enough. So next case that we will see is with the same speed regulation. If the percentage speed regulation of both generators is the same. So with the same speed regulation means the logic is quite simple. That means both of them are having the same speed regulation, and the load shared by the first generator is PA, that will be equal to the total load multiplied by P1, that is rating of the first generator, by P1 plus P2. So similarly, load shared by the second generator would be equal to PL, total load, into P1 plus P1 by P1 plus P2. That means load sharing directly proportional to the megawatt ratings, okay, rating of the generators. Load sharing takes place according to the megawatt rating of the generators. Suppose if megawatt rating of generator 1 is equal to megawatt rating of generator 2, that means both generators are rated at same value, at the same time speed regulation is the same, then maximum load that can be supplied by these generators, by this set, without overloading would be equal to 2 times of generator 1 rating. Okay, now if the generators are having different ratings, so what is the maximum load that can be taken? Even if the generators are having different ratings, then maximum, capacity or maximum load can be taken by the system would be equal to sum of individual ratings. So this much would be enough for this concept of speed regulation. And with this, I would like to close the synopsis part of load frequency control. Thank you for watching.